Let's explore the CYK algorithm, also known as the Cocke-Younger-Kasami algorithm. It is a dynamic programming algorithm used to determine whether a given string can be generated by a context-free grammar. In essence, it checks if a string belongs to a context-free language. Before diving into the CYK algorithm, let's discuss the prerequisites. The most important requirement is that the grammar must be in Chomsky normal form, abbreviated as CNF. A grammar is in CNF if all production rules are in one of two forms. The first form is that a non-terminal symbol, A, can produce two non-terminal symbols, B and C, written as A goes to BC. The second form is that a non-terminal symbol, A, can produce a terminal symbol A, written as A goes to A. The CYK algorithm uses a triangular table to store intermediate results. For a string of length n, we construct an n by n matrix. Each cell in the table, denoted as Tij, contains the set of non-terminal symbols that can generate the substring of the input string starting from position I with length j. The CYK algorithm consists of two main steps. First, the base case. We fill the diagonal cells of the table with the non-terminal symbols that can directly generate the single characters of the input string. Second, we build up the rest of the table by combining smaller substrings using the production rules of the grammar. Here is the pseudocode for the CYK algorithm. The outer loop iterates through the lengths of the substrings from 1 to n. The second loop iterates through the starting positions, I, of the substrings. The variable j calculates the end position of the substring. In the base case, if the length is 1, we find all non-terminals A that can produce the terminal symbol at position I and store them in the table Tij. Otherwise, we combine substrings by iterating through all possible split points k, and check if there is a production rule A goes to BC where B is in Ti, k and C is in Tk plus 1j. If such a rule exists, we add A to Ij. Let's set up an example to illustrate the CYK algorithm. Consider a simple grammar in Chomsky normal form with the following production rules. S goes to AB, A goes to A, and B goes to B. We want to test whether the string AB can be generated by this grammar. Here's the CYK table for our example with the string AB. The bottom row represents the base case, where we fill the cells with non-terminals that generate single characters. T1 1 contains A because A goes to A, and T2 1 contains B because B goes to B. In the next step, we combine these to find non-terminals that generate the substring AB. T1 2 contains S because S goes to AB, A is in T1 1, and B is in T2 1. Finally, let's consider the complexity of the CYK algorithm. The time complexity is big O of n cubed times the size of G, where n is the length of the string and the size of G is the size of the grammar. The space complexity is big O of n squared. This makes the CYK algorithm efficient for membership testing in context-free languages. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.